one and all. I am Dr. Ramya Swetha, Civil Engineering Department from Institute of Aeronautical Engineering. So today our topic is velocity distribution in open channel. So coming to the open channels, the velocity distribution plays in various directions. Most probably in three different ways. In those, we are considering longitudinal only. Velocity distribution is done in three different ways. So velocity distribution is always vary across channel because of the friction along the boundary. The maximum velocity usually found just below the surface. So that is along the flow direction we are considering, along the flow direction of velocity we are considering for velocity distribution. In other two ways, those are not that much insignificant. So that's why we are not considering remaining two velocities for velocity distribution in open channels. In these, velocity distribution through the cross section, this is the lines, this is the section. So we are considering the section. So lines of constant velocity. In these lines of velocity constant, this is the central line velocity profile. This is the central line velocity profile, U and V. Central line velocity profile. We are considering circular. This is rectangular shape, or whenever we are considering the circular shape, this is the cross section we are considering. So this is the velocity profile. This is the velocity profile for open channels. In circular, this is the like this, the velocity profile is occurred based on the center line velocity. Similarly, for the kind of rectangular shape, this is the central line velocity profile we will get. So this is the velocity distribution throughout the cross section. The velocity distribution, it depends upon the direction of the flow and some more parameters which are included. Friction, along the friction with that boundaries. So in that boundary, because of the friction along the boundary, the various the variations will we understand the variations in the below the surface. So like this is the velocity distribution. This is the velocity distribution through the cross section. Shear stress distribution on wetted perimeter also we are considering for the velocity distribution. This is the shear distribution. The previous one is the velocity distribution. This is the shear distribution. In this shear distribution, the dark line, this shows the actual. So this is the dotted is shows the uniform. Uniform shear distribution. Like this, the shear distribution is done along the wetted perimeter. Now, next, the important one is most economical channel sections. What is meant by most economical sections? In channel sections, based on the shape, rectangular, trapezoidal and circular, these are the three different types of channels based on their shape. So, most economical, it means economically those are apt for the given condition. So based on the some parameters, we are understanding the most economical sections. So cost of construction should be minimum, discharge should be minimum, discharge should be maximum, cost of construction should be minimum, discharge should be maximum, and cost of construction should be minimum. These are the two parameters we are considering for most economical section. In that most economical section, various types of channels based on their shape we are classified. Those are rectangular, trapezoidal and circular. So coming to the discharge should be maximum means the wetted perimeter should be minimum. That is the condition we are applying for identifying the conditions for most economical channel sections. In that, the first one is rectangular section. In rectangular section, we may understand most efficient rectangular channel section conditions. Rectangular section. So consider rectangular section. B is the width of the channel. D is the depth of the channel where till the water surface. This is the free surface. Free surface. Consider rectangular channel as shown in figure. B is the width of the channel. D is the depth of the channel. Coming to the perimeter in open channels. Perimeter, this is the perimeter, not overall. Only these three sides, wetted perimeter. So here there is no closed one. So this is open to atmosphere. This is the free surface. It is open to the atmosphere. That's why we didn't consider this is for perimeter. So wetted perimeter for rectangular section is equal to P is equal to D plus B, and again this is also D. This is depth of the channel. B is the width of the channel. Depth of the channel means depth of the water flow. How much the water flow is there. It may vary from here or here. It depends upon the water flow. D is the depth of the water flow. Depth of the flow. D plus B plus again D. This is equal to B plus 2D. This is our wetted perimeter, B plus 2D. Generally, perimeter for rectangular is P is equal to 2B plus D. This is our from mathematically. Mathematically, this is the perimeter. But coming to the open channels, the another side of width of the channel, it is not included, it is open to the surface. So this is the wetted perimeter. So from the above, from the all these, we may get, and we know area is equal to breadth into depth. There is no change in it. So now A is equal to everything comes into one side, every in terms of one parameter. So B into D. So in terms of B in terms of depth, area by depth. The width here, what we understand, the width is equal to area by depth. Width is equal to area by depth. In terms of depth, we are telling the width of the channel. So substituting these values into the wetted perimeter. So now P is equal to P plus 2D, but B is equal to A by D plus 2 by D. B is equal to A by D plus 2D. For most economical channel section, what we understand, discharge is maximum. It means wetted perimeter should be minimum for given area. We are considering most economical channel sections, cross-sectional area should be minimum. So whenever the construction is going to within the less cross-sectional area, the requirements are going to fulfill. So that gives the most economical section. So for that purpose, wetted perimeter should be minimum. So that's why we are considering all parameters in terms of P. We are understanding. So P is equal to A by D plus 2D. So the first one is B is the width of the channel, D is the depth of the channel. We know area is equal to B into D, and the width in terms of depth we are writing A by D, and P is equal to, for wetted perimeter, P is equal to B plus 2D, we substitute in this like this. So this is the one. So now what we did? P should be minimum. It means differentiate P with respect to the depth. Differentiate with respect to depth of the flow. And differentiation, it should be equal to the 0. Minimum means it should be equal to 0. So d by d into d, all terms in terms of d already it is there, a by d plus 2 into d is equal to 0. 2 into d is equal to 0. Differentiation. So a by d is equal to minus a d square by 2 with respect to depth of the flow. It is in terms of with respect to the depth of the flow. It's equal to 0. That is equal to a by d square is equal to 2. That means a is equal to 2d square. So in the condition, as based on the condition, wetted perimeter is minimum. Differentiate perimeter with respect to the depth of the flow, that is equal to 0. So it means area is equal to 2 into d square. Area is equal to 2 into d square. And one more important, we know the thing, mean depth is equal to area by perimeter. We know another parameter, hydraulic mean depth. Hydraulic mean depth, m is equal to a by p. So area we know area, m is equal to a by p. A is equal to 2d square. Area we know the area is equal to, now area p into d. P is equal to b plus 2d. A is equal to b by d. Now in terms of a is equal to 2 into d square. This b, already we know b is equal to in terms of a. A is equal to 2 d square. That is equal to 2d into d. So 2 into d by b. B already b is equal to 2d. So 2d plus 2d. That is equal to 2d by 4d. That is equal to d by 2. M is equal to d by 2. So this is the one of the condition. M is equal to d by 2 is the condition. Here what we understand, minus a by d square by plus 2 is equal to 0, a by d square is equal to 2, a is equal to 2d square, and m is equal to a by p. In this already b is equal to a by d is there, already we know. So we substitute all this, finally we will get m is equal to d by 2. Hydraulic mean depth is equal to d by 2. This is the one of the condition for most economical channel section for rectangular. For rectangular, this is the condition. This is the condition. Hydraulic mean depth is equal to d by 2, or either b is equal to 2 into d. B is equal to 2d and m is equal to d by 2. These are the two conditions which we are going to understand in our thing. How we get, again, a is equal to 2d square, but a is equal to b into d, that is equal to 2 into d square. This is cancelled. This means b is equal to 2d. This is the one of the condition. We apply simply in this mean, hydraulic mean depth. M is equal to b into d plus 2 into d. Already we know b is equal to 2 into d. And finally we will get hydraulic mean depth is equal to D by 2. So this is the condition for most economical rectangular channel section. Rectangular channel section. Finally, for most economical rectangular channel section, conditions B is equal to 2D and M is equal to B into D. It means width is 2 times the depth of the flow and hydraulic mean depth is half of the depth of the flow. Width of the channel in any rectangular section, width of the channel is equal to 2 times of the depth of the flow, as well as hydraulic mean depth is half of the depth of the flow, is the most economical rectangular channel section conditions. P is equal to 2 into D and M is equal to D by 2. These are the final parameters for rectangular channel section condition. Now, next move on to the most economical channel trapezoidal section. So, coming to the trapezoidal section, here also we have to understand some basic parameters. This is the surface water flow, this is the depth of the flow, this is the width, and this is the N into D, 1 into N ratio. So the another side, this is the one side of the trapezoid, that is equal to D into root N square plus 1. This is the which makes an angle theta. So these are the parameters. So most economical channel trapezoidal channel section, let's consider which is the shown in figure. This theta is the angle made with the horizontal, and D is the depth of the flow, B is the width of the bottom of the channel, width of the bottom of the channel. P is the width of the bottom of the channel. In rectangular section, both sides B is equal to equal. Coming to the trapezoidal channel section, width is the width of the top of the channel section is different than the bottom of the channel. Here the B indicates width of the channel bottom channel section. Now, in this, the side slope, in this we can understand in two ways. The one is the side slope is given as 1 vertical and n horizontal. 1 vertical and n horizontal. The side slope 1 vertical, n horizontal, shown in figure. So, in this, the area of the flow, trapezoidal area of the flow, BC plus AD by 2 into D. This is the BC plus AD by 2, average of these two multiplied into D. So we know BC, B. This is our trapezoidal channel section. This is B and the axis is N into D. This is B. Trapezoidal channel section. A, B, C, D. So BC plus AD by 2 multiplied by depth of the flow, that gives the area of the trapezoidal section. So B, we know B plus here this is B. Coming to the top, this is the B. The axis is N into D, N into D. These N into D and N into D is twice. That's why here this is 2 into N into D plus B. This is for AD. This is for AD and 2 into D. So finally 2B plus 2ND by 2 into D. So B plus ND by 2 into D, that is equal to 2 to cancel, B plus ND into D. This is the area of the trapezoidal channel section. And A by D is equal to B plus N into D also. We can write like this also the equation. Similarly, B is equal to A by D minus N into D. N into D. Width of the channel section in terms of depth of flow and area. So this is equal to B is equal to A by D minus N into D. Now coming to the wetted perimeter. Coming to the wetted perimeter of the trapezoidal channel section. Coming to the wetted perimeter trapezoidal channel section. So this is A, B, C, D. Shown in figure. This is A, B, C, D. So coming to the wetted perimeter, perimeter P is equal to AB plus BC plus CD. This is the wetted perimeter for given trapezoidal channel section. Wetted perimeter. This is the wetted perimeter. P is equal to AB plus BC plus CD. So this is the thing. In this, AB plus BC plus CD, and one more important thing, these two are same. AB and CD both are same. So it means BC plus 2 into CD both are same. AB and CD are same. Now B is equal to AB plus BC plus CD both are same. So BC plus 2 AB or 2 CD. Whichever is no issues. Whichever we consider, no problem. So here I am considering BC plus 2 into CD. Why? Because AB is equal to CD. Now we know BC. BC is simply it is width of the channel bottom. So that is B. Coming to the CD. This is nothing but again we have to understand here. So we triangle, right angle, triangle. This is ND, this is D. So finally this is equal to D root n square plus 1. D root n square plus 1. This is n into D. So C square plus 2 into root C square plus DE square. C square 2 into root C square plus DE square. Substitute in this. Finally we will get wetted perimeter P is equal to B plus 2D root n square plus 1. P is equal to 2D root n square plus 1. So substitute the value of the B. Substitute the value of the B into this. Finally we will get substitute the value of P. P is equal to P plus 2D root n square plus 1. Substitute the value of the B from 2. So that is equal to A by D minus ND plus 2D root n square plus 1. All in terms of D, depth of the flow. So that is equal to A by D minus n into D plus 2D root n square plus 1. For most economical channel section, P should be minimum. It means differentiate with respect to depth of the flow is equal to 0. That is the condition. So differentiate with respect to D, wetted perimeter, differentiate the equation 3. This is the equation 3. This is equation 3. Differentiate the equation with respect to. So now the differentiation minus A by D square minus n plus 2 into root n square plus 1 is equal to 0. Here n is the constant. So A by D square plus n is equal to 2 root n square plus 1. 2 root n square plus 1. Substitute A by D square plus n is equal to 2 into n square in the equation 1. Substitute in this. So substitute after substitution A by D square plus n is equal to 2 root n square plus 1. So substitute the equation in equation. Substitute this equation A from equation 1 in the above equation. So finally what we will get? B plus nd into d plus d square plus n is equal to 2 root n square plus 1 is equal to b plus n into d by d plus n into 2 root n square plus 1. This is it. And after that finally b plus, this is the thing, b plus nd by d. B plus nd by 2nd by 2 is equal to half of the top width. It represents the half of the top width. B plus 2nd by 2 is equal to half of the top width. D root n square plus 1 is equal to CD. That is one of the sloping side. This is one of the sloping side. So from the above equation is required a condition for a trapezoidal section to be most economical, which can be expressed. It means half of the top width must be equal to the one sloping side of the channel. Half of the top width must equal to the one side sloping side of the channel. This is the one of the condition for trapezoidal channel section. Similarly, based on next hydraulic mean depth. Hydraulic mean depth is equal to m is equal to a by p. So a is equal to b plus n into d. So p is equal to p plus 2d root n square plus 1. That is equal to b plus 2nd also. So finally b plus 2nd is equal to 2d root n square plus 1. It means 2b plus 2nd is equal to 2b plus nd. Mean depth m is equal to a by p. That is equal to d by 2. Finally, after the calculations. So here also hydraulic mean depth is equal to half of the depth of the flow gives the most economical channel section. Here for trapezoidal channel section we have two conditions. The one is trapezoidal channel section to be most economical, which can be expressed as half of the top width must be equal to the one of the sloping sides of the channel, and the second one is based on the hydraulic mean depth is equal to half of the depth of the flow. In this half of the depth of the flow, both are the similar conditions which are going to apply in both rectangular and trapezoidal channel sections. And the next one is trapezoidal channel section. The another condition is the three sides of the trapezoidal channel section of the most economical sections are tangential to the semicircle. So it is we can prove based on like this. This is the thing we are going to understand. In this draw, consider in the top of the trapezoidal channel section at midpoint, at center of the top width. At center of the top width, consider it as O. Draw perpendicular to the along the side of the AB. Draw perpendicular from midsection of the mid of the top of the channel to draw perpendicular from there to sloping side AB. AB. So triangular OAF. This is OAF. Makes an angle theta. It's a right angle triangle. So in this, sin theta is equal to OF by OA. OF is equal to AO sin theta. In this triangle AEB, this is also AEB. This is the one of the triangle. This is the another triangle AEB and OAF. Those are the true triangles. So in this, coming to the triangle AEB, from AEB, sin theta is equal to AE by AB. Sin theta is equal to AE by AB. Sin theta is equal to AE by AB. This is the formula from triangle AEB. Sin theta is equal to AE by AB, D by root D square plus N square D square. So this is from D by D root 1 plus N square. N square, D cancel, finally 1 by root 1 plus N square. Substituting sin theta is equal to 1 by 1 plus N square whole root in equation. So now OF is equal to AO into sin theta, that is nothing but 1 by 1 plus N square. AO is equal to half of the top width. Half of the top width, it means B plus 2ND by 2, that is equal to D root N square plus 1. So substituting these values of AO in the above equation, finally we will get OF is equal to D by root N square plus 1 by root N square plus 1. So OF is equal to D, it is nothing but the depth of the flow. It is nothing but, so the depth of the flow is equal to the OF. Depth of the flow is equal to the OF. So B plus 2ND by 2 is equal to D root N square, D root N square plus 1. M is equal to D by 2. A semicircle drawn from O with radius equal to the depth of the flow will touch the three sides of the channel. These are the conditions for most economical trapezoidal channel sections. Trapezoidal channel sections. Hence, so thus if a semicircle is drawn with O as center and radius equal to the depth of the flow, radius is equal to the depth of the flow D, the three sides of the most economical trapezoidal section will be tangential to the semicircle. So these are the most economical trapezoidal sections are, the one is B is equal to 2 plus 2ND by 2 is equal to D root N square plus 1. Hydraulic mean depth is equal to half of the depth of the flow. Semicircle drawn from half center point from the top width with radius equal to the depth of the flow will touch the three sides of the channel. So this is the for trapezoidal channel section. This is for trapezoidal channel section. Area of the trapezoidal channel section. This is the area, and these are the equations already we gone through. Perimeter P is equal to P plus 2D root N square plus 1. Substituting. So this is the equation for most economical trapezoidal section. Depth of the flow B and area A is the only variable. Besides slopes will be when section is most economical, or in other words P is the minimum. For P minimum value we have dP dN. In previous we understand with respect to the depth of the flow, here in terms of N, in terms of slope of the side of the channel. So most economical channel section wetted perimeter differentiate with respect to the depth of the flow. These are the conditions. Coming to the in terms of slope of the side, side of the channel. So what will happen? We will go see. So D best side slope of the most economical trapezoidal channel section. So dP by dN. So coming to these are the equations already we know. This is equation 1. Area of the trapezoidal section A is equal to B plus ND whole into D. This is equation 1. Similarly, wetted perimeter of the channel P is equal to B plus 2D root N square plus 1. And substitute the B from equation 2. Already we know this equation. So finally, this is the equation 3. Now substitute, hence differentiate the equation 3 with respect to side slope. Side slope of the channel. So this is the equation we will get. So dn with respect to the n. So finally cancelling and dearranging, finally we will get 2n is equal to root n square 1, and again substitute both the terms. Finally n is equal to 1 by root 3. If the side slopes makes an angle theta with the horizontal, then we have tan theta is equal to 1 by n, that is equal to 1 by root 3. It means 60 degrees. Hence, the best side slope is at 60, that horizontal or the value of n, the best side slope is the given by this equation. So, wetted perimeter is differentiated with respect to the depth of the flow. We have already known those conditions. 3. So, wetted perimeter with respect to side slope, n is equal to 1 by root 3, 60 degrees. The best side slope at 60 degrees to the horizontal. From that, half of the top width is equal to length of the one of the side slope. That is already known condition for us. From this, substitute the value of n from the above equation. From the above equation, substitute the n. So finally, we will get this one. Wetted perimeter. So finally, length of the sloping side is equal to the width of the trapezoidal channel section. Length of the siding slope is equal to the width of the trapezoidal section. This is the trapezoidal channel section, most economical trapezoidal channel section. Next, the next one is most economical circular channel section. Flow through circular channel. The flow of liquid through a circular pipe when the level of the liquid in the pipe is below the top of the pipe also comes under open channel. It is also classified as open channel flow. The rate of flow through circular channel is determined from the depth of the flow and angle subtended by the liquid surface at the center of the circular channel. Here d is the depth of the flow, 2 theta is the angle subtended by water surface AB at center in radius, r is the radius of the channel. Thus the wetted perimeter is determined. So wetted perimeter P is equal to 2 pi r by 2 pi into 2 theta is equal to 2 r theta. Perimeter P is equal to 2 r theta. Perimeter P is equal to 2 r theta. Wetted area. Here also, till now what we consider area, but coming to these circular section, wetted area. So area is equal to, this is the area, AC, B, D, AD, BA. This is the area we are considering, that is nothing but wetted area AD, BA. So area of sector OADBO, area of triangle minus area of triangle ABO gives the wetted area. Area of sector OADBO and area of triangle ABO gives the wetted area. This is the wetted area after all the calculations. The calculations, area of the sector, that is equal to pi r square by 2 pi multiplied by 2 theta. Area of triangle AB into CO by 2, that is equal to r square theta minus 2 BC into CO by 2, because AB is equal to 2 BC. AB is equal to 2 BC. So fine, BC is equal to r sin theta, CO is equal to r cos theta. BC is equal to r sin theta, CO is equal to r sin theta from the figure. So coming to the hydraulic mean depth, M is equal to A by P, that is equal to r by 2 theta, theta minus sin 2 theta by 2. So discharge Q is equal to AC root MI as from Chise's constant. So most economical circular section, we have two conditions. One is condition from maximum velocity and condition from maximum discharge. Condition for maximum velocity and condition from maximum discharge. The first point based on the maximum velocity. So velocity V is equal to C root Mi. Here M is equal to A by P. So here V is equal to C root Mi, where M is the hydraulic mean depth. So with respect to theta, differentiate area by perimeter is equal to 0. A and B are both are the functions of theta. Both are the functions of theta. The value of etted perimeter A is given in the equation. And the value of etted perimeter B is equal to P 2R theta. So differentiating equation with respect to theta, finally what we with respect to theta, that is gives the P dA by d theta minus A into dP by d theta divided by P square is equal to 0. Finally, from substituting all the equations, using all the equation, finally dP by d theta is equal to 2R. And substitute the velocity of the flow through a circular channel is maximum when the hydraulic mean depth M or A by P is maximum for a value of C and I. In case of circular pipe, the variable is pi only. Hence, for maximum velocity A by P, we have the condition. We have this condition. So finally D is equal to 0.81 into D. Here capital D is the diameter of the circular channel. Capital D is the depth of the flow. This is the capital D is the diameter of the circular channel. Maximum, based on the maximum velocity of flow, the depth of water in the circular channel should be equal to 0.81 times of the diameter of the channel. Depth of the flow, depth of water in circular channel should be equal to 0.81 times of the diameter of the channel. So from all the calculations, we will get this final condition for the circular channel based on the velocity. Hydraulic mean depth for maximum velocity. So this is the M is equal to A by P. Substitute area and perimeter in terms of theta. Finally, we will get 0.611 R and 0.3 into T. Thus, the maximum velocity, the hydraulic mean depth is equal to 0.3 times of the diameter of the circular channel. The next condition is condition for maximum discharge for circular section. These two are the conditions for based on the condition for maximum discharge for circular section. Those two are the one is D is equal to 0.81 into D. Depth of flow, depth of the water in circular channel is equal to 0.81 times of the diameter of the channel. Condition and the other one is M is equal to 0.3 into D. Hydraulic mean depth is equal to 0.3 times of the diameter of the circular channel. These are the two conditions for maximum velocity, for the condition of maximum velocity of a circular section. Now coming to the maximum discharge. Another condition, second condition, maximum discharge. So Q is equal to Cheese's formula Mi. In this, the discharge will be maximum for constant values of C and I when A to the power of 3 by P is maximum. A to the power of 3P will be maximum when with respect to theta. So in that, differentiate with respect to theta, that should be, and equation the same to 0, finally we will get dp by d theta is equal to 2r, and but p is equal to 2r theta, dp by dr is equal to 2 theta, and substitute. Finally, we will get the depth of the flow for maximum discharge. D is equal to 0.95 d. After doing the solution, the final one is D is equal to 0.95 into D. Thus, for a maximum discharge through a circular channel, the depth of the flow is equal to the 0.95 times to its diameter. This is the one condition based on the discharge, maximum discharge. Maximum discharge through a circular channel, the depth of the flow is equal to 0.95 times into 95 times to its diameter. This is the conditions we will get in most economical channel sections. These are the three major sections we have. The one is rectangular channel, and the second one is the trapezoidal channel, and the third one is the circular channel. These are having their own conditions for getting the economical sections. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.